Okay, so today what I'd like to do is we'd like to practice looking at a non-standard trajectory or projectile motion. The trajectory actually will be the same. It's going to be our parabola. But let's imagine that we have something like a bird or a rocket or something that's able to provide thrust in such a way that the speed along this trajectory is constant. Now, normally during projectile motion, you slow down as you go up and then you speed up as you come back down. But let's say that we just have a constant speed the whole time. The question we want to ask ourselves is, what is the acceleration at any point along this curve? And in particular, what's the acceleration at the vertex? So the first thing we want to recall is the actual trajectory formula. So that is the actual path through space. That hasn't changed. But this v naught is now going to be the speed actually the whole way through the trajectory. And we want to know what the acceleration is. So the first thing we want to recognize is that at any point along this trajectory, the derivative of the trajectory will be the tangent of the angle that the trajectory or velocity vector makes with the horizontal at that point. So I'll call that tan theta. And notice that that theta is generic, whereas theta naught is the launch angle. And then we should also be able to see that this is the same thing as y dot over x dot. It's the ratio of the y velocity to the x velocity at that point. We can see this pretty easy geometrically if we just pick a random place. Let's say here's v at some later time. Notice that this would be my angle theta. And from this right triangle, x dot would be vx, y dot would be vy. And of course, tangent is just going to be opposite over adjacent there. Okay, knowing this, we can then write down what x dot and y dot are. So x dot is supposed to be the component of the velocity in the x direction, which remember is going to be the speed times the cosine of that angle, but the speed is constant. So this will just be v naught cosine theta, and y dot will just be v naught sine theta. Now we can rewrite these sines and cosines in terms of the spatial derivatives of the trajectory, which we have. So the easiest way to determine this cosine is probably to use the Pythagorean identity. Remember that sine squared plus cosine squared is 1. I want to write things in terms of tangent, so I'll divide everything by cosine squared and get our other Pythagorean identity. Tan squared plus 1 equals secant squared, but that's 1 over cosine squared. So solving for cosine, we get that this is going to be 1 over the square root of 1 plus tan squared. And similarly, if I want sine theta, the easiest thing to do is just say sine is tangent times cosine. So we'll just multiply this whole thing by tangent. And now we can rewrite this as v naught times 1 over root 1 plus tangent squared, but tangent is y prime. And similarly, v naught sine will be v naught y prime over square root 1 plus y prime squared. So now we've been able to rewrite our time derivatives of position in terms of these y primes, the spatial derivatives of our trajectory. Now, we're not really after the velocity components. Well, we could be, but we're really after is the acceleration. So we're going to have to take another time derivative here. And to do this, let's use the chain rule. Notice that if I want, say, x double dot, so the x component of the acceleration, this is the time derivative of x dot. But I can use the chain rule to rewrite that as the x derivative of x dot times dx dt. But of course, dx dt is just x dot. Oops. We use this trick all the time to turn time derivatives into spatial derivatives. So now I can see, oh, okay, well, I just have to take my x dot, which is here, and then take an x derivative of this to get my acceleration. So let's do that. X dot is as given, so v naught, I'll put the square root here. To take an x derivative of this, well, v naught is still a constant, so that's not a problem. But we're going to have to use the chain rule in a couple different ways. So I'll do it. This is all to the minus 1/2 power, so I'll bring down a minus 1/2. We have 1 plus y prime quantity squared to now the negative 3/2, doing the derivative rule, power rule. Then on the inside, I want the derivative of this with respect to x. I'll get a 2, I'll get a y prime, and then don't forget y prime itself depends on x. That'll give us y double prime. If we clean this all up a little bit, we can see that the 2's cancel. V naughts combine to give us a v naught squared. And then this negative 3/2 power and this negative 1/2 power give us a negative 4/2, which is, of course, negative 2. So I can rewrite all of this as an overall minus sign. Let's not forget that. V naught squared y prime y double prime over 1 plus y prime squared squared. So that's our expression for the second derivative in x. I will now bring this to the top, and I will also write down what the second derivative is with respect to y. It's a very similar thing. Just notice that here it's a little more complicated because we do have a quotient. So I'll have to use the quotient rule. I'll pick up another y double prime type thing. But all of that also simplifies, so I'll just write the result at the top of the next board. Okay, so once you simplify that all out, here are the expressions we get. Notice they have the same denominator. They both have a y double prime, so they should depend on the curvature of the trajectory. Y double dot is actually a positive number. Well, I shouldn't say that. Y double prime will be negative because it's concave down, but there's no extra negative sign here. And now we want to calculate the acceleration. We're actually done. That is the acceleration, but we probably want to write it in terms of these initial parameters. So I do need to calculate y prime and y double prime from my trajectory. So taking the first spatial derivative will give me a tan theta naught. This 2 will cancel and give me just gx over v naught squared secant squared theta naught. And then a second derivative, that term is a constant, it'll go away. We just have a linear term. As mentioned, it is a negative number because this is concave down. All these things are positive. And now we could just plug all of these in to our expressions here and get some formula that tells us the accelerations as a function of x. This x will show up here, and it'll show up here, and it'll show up here. The y double prime is a constant that could be factored out of all of this. The result is not terribly illuminating. You can slightly simplify the denominators, but it's still kind of a little ugly, so I won't write down the general version. But I do want to look at the special case of x equals the halfway points, the half range, because that tells us what the acceleration components are at the very top of the trajectory. I also want to notice that the magnitude of the acceleration, which is the Pythagorean combination of these, maybe I'll set that over here somewhere. So just note that a, which is the square root of x double dot squared plus y double dot squared. And again, I could write down this common denominator, which is under the square root. And then upstairs, we'll have this v naught squared, which will come out of the square root once we square each term. Notice also, you might think, okay, what about these? They do both have a common factor in the denominator. I pulled it out of the square root with that square, so that's what's left behind. And then this will become 1 y prime squared, y double prime squared. This will become a y double prime squared. So I can leave let's leave it as a magnitude of y double prime, just because we do know it's actually negative in this case. And then the 1 plus y prime squared will partially simplify with this. Maybe I'll even just leave the y double prime here. And then we will get a single square root in the denominator. And this should look kind of familiar. This is exactly the curvature, which will be a function of x, times v naught squared. In other words, the magnitude of the acceleration is proportional to this constant speed that it has the whole time, but it's proportional to the curvature of this parabola as a function of position or time, whichever way you want to write it. And we've previously calculated the curvature of a parabola on this channel. So I'll leave that off to the side. But let's go ahead and look at what happens at that midpoint. So notice we already know that at this middle point, the derivative y prime must be 0. So I don't really have to worry about that. Y prime will be 0. So that tells me that at the vertex, x double dot is 0. That shouldn't be too surprising from symmetry. We can also see that as this projectile is rising, first it's accelerating to the right, because y double prime is always negative, y prime is positive on the initial part, and there's this minus sign here. The denominator is, of course, positive. So it's accelerating to the right. That's to make sure that it maintains a constant speed total. That doesn't mean that its x component necessarily stays constant. It doesn't. In the normal case, it does when we don't have any enforced constant speed. But here, we do have to accelerate as we're moving up. Then at the top, where there should be no acceleration, which is what we get in the x direction. And then as we're coming back down, we have to have a negative acceleration so that it doesn't increase its speed due to that gravitational pull. So that's not so bad. To find the y component, I need to know what y double prime is. We already know what it is. And I do need to plug in what x equals the vertex is. But again, y prime is 0 there, so I don't really have to go plug it into the formula. So we'll just have that y double prime is v naught squared times this negative g secant squared, which is negative g secant squared theta naught. So notice that if it was a standard case where this is just flying through the air and doesn't have any extra thrust that's keeping the speed constant, we would just get a minus g. That would be the acceleration at all times. But now we see that that acceleration does change. And in fact, at the top, where it's rounding the bend pretty quickly, we augment that by an extra factor of secant squared theta naught, which is greater than 1. So we know that it's going to have a larger than g acceleration coming over the top of that. And you've maybe felt this same sort of thing on a roller coaster or something. If you're coming over the top of a hill at constant speed for whatever reason, maybe there's brakes or thrusters or something that are keeping you going, you really do feel that that acceleration more greatly because you're being forced to move at constant speed. At any rate, we now have our acceleration at the top of the trajectory. We at least implicitly have the accelerations at any point on the trajectory as long as you plug in a random value of x here, including at the initial and ending points. And we can see that the acceleration generically for a constant speed curve, or at least this constant speed curve, will be proportional to the curvature. I should note, we derive this in full generality. I never used the specific curve that we're dealing with, so this actually is general. Any curve where you're moving at constant speed, you can calculate the magnitude of the acceleration. One last thing we could check is how the acceleration and velocity vectors are related. Let's go ahead and take the dot product of the velocity and the acceleration, which would be x dot x double dot plus y dot y double dot. On the previous board, we had those values. I'll rewrite them out real quick here. And we can quickly see that if we take x dot, multiply it by this, y dot, multiply it by that, both numerators will have a y prime. The denominators will be the same. I guess it'd be 5 halves power now, a half and then a 2. But this has a negative sign. So these add to 0. In other words, if you're moving at constant speed, your velocity and your acceleration must be perpendicular. That kind of makes sense intuitively, because if our speed is constant, then our tangential acceleration, which would be the thing that changes our speed, must be 0. Hence, the only component of the acceleration should be normal, changing the direction. And that's kind of what we just showed, that the acceleration is perpendicular to the velocity at all times. And I think that's a pretty good analysis of our constant speed parabola. QED.